Okay, folks, so you should have at least the first three columns filled in. I would like you to take a minute to go ahead and use what you know from the first three columns to come up with the atomic number. So use what you know from the first three columns to come up with the atomic number. Next, I want you to use what you learned in the first three columns to come up with the mass number. Mass number. And then finally, you're going to use your periodic table, which hopefully you have open in a second tab. You're going to use your periodic table and your atomic number to figure out what element each of these models represents. Okay, with the chart all filled in, hopefully you noticed something a little odd. We had completely different atoms, but there were 2 atoms of chlorine. There were 2 atoms of lithium and 2 atoms of phosphorus. But the question is, were they the same? And the answer is, not quite. So let's start with chlorine up here, and let's compare some of our numbers for chlorine. We'll use green for chlorine because chlorine is a green gas. All right, let's find the things that are different between the 2 models that we had for chlorine. So both of them had 17 protons. So that was not different. Ooh, here's a difference. It had 18 neutrons in one model and 20 in another. So that's different. Okay, 17 electrons, 17 electrons. So that was the same. Atomic number, 17 and 17, that's the same. Mass number is different, which if we have a different number of neutrons, that should probably make sense. Because remember, protons plus neutrons are what get us the mass number. So if the neutrons are different, the mass number is going to be different. And then of course the element is the same. So let's look at our second pair of isotopes, our 2 lithiums. I'm going to use purple for lithium, okay? So let's start over here. Protons, 3 for both. Neutrons, 3 and 4. So this is different. So let's highlight this difference. One isotope had 3 neutrons, the other isotope had 4. All right, let's keep going. Electrons are the same. Atomic number is the same. Mass number is different, which again, that should make sense because mass number is protons plus neutrons. If the neutrons are different, the mass number is going to have to be different. All right, and then of course the element is the same. All right, let's look at our last one. Let's look at phosphorus. I'm going to use blue for phosphorus. Let's look at our 2 atoms of phosphorus. Protons are the same, 15 and 15. Neutrons are different. Okay. 15 and 16, so we have a different number of neutrons in our 2 different isotopes. Electrons are the same. Atomic number is the same. Mass number is different, which again should make perfect sense because mass number is protons plus neutrons. If the neutrons are different, this is going to be different too. Okay, so let's flip our notebook over to page 30. So what is an isotope? What is an isotope? Ooh, goodness, Miss Crane's small handwriting. Let's zoom that in a little bit for you. Okay, so what's an isotope? Well, what did we notice was different? Neutrons and mass. So it is atoms of the same element with different masses because they have different number of neutrons. So that, ladies and gentlemen, is what an isotope is. They are atoms of the exact same element that have different masses, their mass number, because they have a different number of neutrons. Now you'll notice they're all still the same element. So over here on our chart, because the protons didn't change, it's still chlorine because it's the protons that determine the atomic number, okay? And the atomic number determines what element it is. So since the protons aren't changing, the element doesn't change, okay? If we have a differing number of protons, and this does happen in a nuclear reaction. In a nuclear reaction, we can lose protons as a type of radiation, okay? But when that happens, chlorine wouldn't still be chlorine, okay? So if we lose protons due to a nuclear reaction where our nucleus falls apart and we lose protons, it's actually going to change what element it is. It's called transmutation, okay? Our electrons didn't change, okay? Electrons can change, but that is when we make ions. That happens during an ionic bond where we have an exchange of electrons going on. So what makes something an isotope is when they have a differing number of neutrons. And this occurs naturally in nature. Okay, so if I take a sample of chlorine, I am going to find multiple chlorine isotopes in my sample, okay? If I take a sample of carbon, there's gonna be carbon 12, there's gonna be carbon 13 present. In fact, that is how we actually are using carbon dating to determine how old certain things are, is because of the different isotopes and how much of them they have. So when we find this in nature, we have what's called the percent abundance. And the percent abundance is what percent of any sample is a given isotope. Okay? So we have this concept called the percent abundance, and it's the percentage of any sample that is a given isotope. So let me give you an example. Okay, so chlorine I'm going to use chlorine because it's very simple. It's only got 2 major isotopes. Okay, so chlorine, any sample of chlorine I take is going to have chlorine 35, and chlorine 37. Okay, how much of each? Well, it depends on my sample, but I know what percentage should be chlorine 35. Chlorine 35 has a percent abundance of 75.78%. That means that about 3/4 of all of the chlorine atoms in my sample are chlorine 35, 75.7%, okay? So that's about 3/4. I'm rounding it down a little bit. About 3/4 of my sample of chlorine is gonna be chlorine 35 atoms. The other fourth, or 24.22%, is going to be chlorine 37. So even though it's all chlorine, the individual chlorine atoms are actually different. 3/4 of them are going to be chlorine 35 with only 17. That's right. Okay. So 75% are going to be chlorine 35. And so they're going to have 18 neutrons. And then chlorine 37 is going to have 20 neutrons. Okay? So why do we care? Why is this so important? Well, you remember how I told you that the mass number is not on the periodic table, and this is why. because every element has multiple mass numbers because it has multiple isotopes. Chlorine is pretty simple. It only has 2. A whole bunch of them have a lot more than 2, and they wouldn't all fit on our periodic table. Also, these numbers are not terribly useful because when I take a sample of chlorine, it's going to have both in there. And so what I really need to know is what's going to be the mass of the sample I take. And that, ladies and gentlemen, is the information that's on here. You'll notice that chlorine, let me zoom that in just a bit. There you go. Chlorine is 35.453. We are closer to chlorine 35 because there's more of it. But we're not right at 35 because we do also have some 37, which affects the average mass of any sample a little bit. So it makes it slightly more than 35. Okay? So this number here is a weighted average. We take this mass and we multiply it by this percentage. We take this mass and we multiply it by this percentage, and then we add them together, and that gets us our average atomic mass, which is what we put on the periodic table. So that's why mass number and average atomic mass can't be used interchangeably, because they are very different. We use our mass number for each of the different isotopes with the relative abundance to calculate the average atomic mass. And that, ladies and gentlemen, is what we are going to be learning how to do later the week.